So there is a complete agreement between what and what. On the one hand, Laplace, and on the other hand, state space. Okay? And this is very good news, because at least our algebra did not betray us. What I would like to do now is first you to believe me that this is always the case. Second, what I want is to take, is to look at some other problems. So as I said, we are interested in getting like the most general formula for the time domain solution to the dynamical system. Remember, the solution is given in terms of x of t is equal to e to the at times x0 plus integral from 0 to t of e to the minus a tau u of tau d tau. Okay? And then y is just equal to c times x of t plus d times u. So what we want to understand is what's in this a. Now here's a theorem. Let's begin first with a diagonalizable. That's a particularly easy case. What we write is that we have a P such that A equals P A tilde P inverse. The columns of P, and A tilde is diagonal. Okay, so we have A tilde, which is lambda 1 through lambda n. Some of the lambda i's might be complex. Don't forget that. Then what? Then the columns of P are the eigenvectors. Okay, so columns of P are the eigenvectors that correspond to A tilde. So now what I can do is, using some thing that we have studied before, we can write that e to the at will simply be equal to p times e to the a tilde t times p inverse. Now, since a tilde is diagonal, this will simply be equal to e to the lambda 1 t. So the matrix made of the diagonal entries e to the lambda 1 t all the way through to e to the lambda n t, with zeros everywhere else, such that we have a general expression for x, and it will read as follows. I can do it again. It will be x of t is equal to p times e to the lambda 1 t all the way down to e to the lambda n t times p inverse times x0 plus integral from 0 to t of p times e to the lambda 1 tau all the way down to e to the lambda n tau with a minus in front of it times p inverse times u of tau d tau, which I can write as also as x of t is equal to p times this bunch of exponentials e to the lambda 1 t all the way down to e to the lambda n t 0, 0 times p inverse x0 plus p times integral from 0 to t, and I'm going to place this guy inside that integral to get the diagonal matrix e to the power lambda 1 times t minus tau all the way down to e to the power lambda n times t minus tau times p inverse times, I forgot a b, u of tau d tau. So in a way, that is the most general expression you can get to write the expression of x of t and therefore y of t, which is just c times x of t, if the matrix is diagonalizable. The worst you're going to see is exponentials in front of x0 and integrals of exponentials times u there. For example, if u happens to be an impulse, the expression you will get is something like this. You will get, if u is an impulse, x of t will be equal to p times e to the lambda 1 t all the way down to e to the lambda n t 0, 0 times p inverse times x0 plus plus what? Well, all these exponentials are going to go down to 0, and we will just obtain plus b, plus e to the lambda, sorry, let me replace and rewrite this as p e to the lambda 1t all the way down to e to the lambda n t 0, 0 times p inverse times b. So what this does is that it gives you some idea about how complicated x of t and therefore y of t as well can be for certain inputs, okay? And you see that you don't see much worse than exponentials. Of course, sometimes we will have exponentials of complex numbers, but nevertheless, exponentials, okay? So what you have is a very good view of how complicated things can get. Now, let's look at the more general case. Because one thing is that not all matrices A can be made diagonal. So, in which case we need something else. Well, what we have is a not very practical but theoretically useful way of discussing A, which is the so-called Jordan form. If you take, what happens is that you can always write as A is equal to P times A tilde times P inverse. But A tilde, instead of being diagonal, will be made of things like this. It will be block diagonal, and the blocks will have a very peculiar shape. Okay? There can be an arbitrary number of blocks as long as they don't grow beyond the dimension of the matrix. But inside the blocks, each block is going to be either something like that, or a number, or maybe two repeated numbers and a 1 there, or in more general form, a bunch of numbers on the diagonal, a 0 underneath, a bunch of 1s on the first diagonals, and 0s everywhere else. That is the Jordan form.